Greetings and welcome to Section 9, where we'll be discussing the terrestrial atmospheres. And the image we have in our astronomy picture of the day, we're looking at the image of a red sprite, a phenomena that's difficult to picture. This might be one of the first images ever taken of one, and it's showing basically a rare type of lightning strike from the cloud to ground, ions moving around. As usual, let's just start off with a simple question. We're going to ask ourselves, hey, if there was no greenhouse effect on Earth, what would happen to our oceans? Go ahead and pause, think it over, and come right back. It turns out that without greenhouse gases on Earth, the planet would be too cold. The oceans would literally freeze over. So the surface temperature of this planet would be too cold to sustain liquid water and definitely be able to sustain us. So there is a certain amount of greenhouse gases that we do need to survive on this planet. So the topics we're going to cover in Section 9 are going to be discussing the primary and secondary atmospheres of the terrestrial objects and the related greenhouse effects on them. We'll look at the layers of the atmosphere, explicitly about Earth's atmosphere, and talk about atmospheric circulation. That's a fancy way to say wind. Then we'll compare Earth's atmosphere to other atmospheres of terrestrials, and we'll end about climate change. And before we get all of that, I have this wonderful picture that I love here. This was taken from the International Space Station, and this is a picture through Earth's atmosphere of the moon. Some quick facts about the planetary atmospheres that we've seen. Mars has an atmosphere. We actually detected about a decade ago at the time of the recording of this video, that there was this excess methane release in the atmosphere of Mars. As for the Mercury and Moon, they have what we call these exospheres, which are effectively no atmospheres at all. And coming down to, they're mainly objects. Sometimes there's gases trapped underneath, going back to the examples of the Mercury and Moon. Sometimes you'll talk about gases that are trapped underneath the layers of the surface. And that can be liberated, that can come forth and reach the surface. But neither one will be able to retain those gases that are trapped underneath the surface. The Moon, those gases just float away. The moon isn't massive enough to have a gravitational pull on those materials. And Mercury is just too hot. These gases, as soon as they break free of the surface of Mercury, they just float away. Now, the remaining terrestrials, Venus, Earth, and Mars, they definitely have what we're going to call significant secondary atmospheres. So pulling our nebulous model back into the picture here, remember we discussed how the gas cloud, the nebulous, formed into a protostar at the center and this protoplanetary disk. Well, this is going to be mostly hydrogen and helium gases. And when the young planets formed, they'd have with them these primary atmospheres. So we're still discussing just the terrestrials. So these will be the solid rocks at the cores of these young planets. And they'll have an atmosphere of, once again, hydrogen and helium around them. And this is what we'd call their primary atmospheres. Some might refer to the first atmospheres of these planets. Just all the gases that are going around, that are swirling around them from the protoplanetary disk. And a lot of that atmosphere came from accretion. Just the protoplanetary disk coming around, collecting together from gravitational forces. Don't forget the angular momentum making them spin faster and faster. And you'll have that first round of atmospheres. Once again, hydrogen, helium. All of the terrestrial bodies lost this primary atmosphere. Every single terrestrial body no longer has a primary atmosphere for a couple of reasons. The biggest argument is just to effectively say the gases got so hot that they floated away from the planets. They were so energetic from their own internal thermal energies and the radiation from the sunlight that caused these gases to get too excited that the planets could no longer hold on to these primary atmospheres. So what does it that we mean that the gases could float away? Let's define some properties. If you take the temperature of a gas, that's effectively a measure of the average kinetic energy of the molecules in that gas. And a expression describing this says that the velocity of a gas is equal to the square root of 3 times what's called the Boltzmann constant, T, the temperature of that gas, divided by the mass of the molecule. So the Boltzmann constant, and it's a property of gases, and it's this simple 1.38 times 10 to the minus 23rd. This is joules per Kelvin. That's a energy per unit temperature. So when we read this expression here, the velocity of a gas, what we're effectively saying is that, hey, the hotter the gas is, the higher the temperature, the faster that gas is going to be moving around. Well, rapidly moving gases in an atmosphere, well, that creates pressure. So pressure is just this combination. I'd say the pressure is proportional to how dense the cloud is times the temperature, right? Higher temperature means they're moving around quickly. Higher density means that these gas molecules are constantly bouncing off each other. So if they have a high temperature and a high density, you can get this feedback, this expanding outwards. That's what happens when you have this pressurized object. And remember, all the way back to section 4, we said, hey, whenever you are an object orbiting a gravitational body, there is this corresponding escape speed, the amount of speed you need to move at in order to break free of the gravitational pull of that planet. And it was just 2 times the universal gravitational constant, the mass of the planet that you are bounded to, and the radius, how far away from the center of that planet you are. We never once specified how massive your orbiting satellite had to be to escape back in section 4. All we said was, hey, if you move fast enough, if the speed of the gas is greater than the escape speed of the planet, the gas floats away. It leaves. Let's look at the plot of escape velocity versus the surface temperature of the planet. And let's start with the planet that matters most to us, Earth here. So at Earth, in order to escape the planet, you need to be moving at around 10 kilometers a second. Let's go ahead and draw that in here. So if you want to fly off the surface of Earth, you're going to be going about 11 kilometers a second. We'll update my previous answer. So you're moving at 11 kilometers a second. You get to escape Earth, fly away. Now look at helium. Helium, when it's heated up to around 110 Kelvin, it'll be moving around at this 11 kilometers a second. So if helium is any hotter than 100 Kelvin, it'll be moving too fast. It will escape Earth. See how the helium-hydrogen bands are above here? What this says is that when helium is at 100 Kelvin, it's moving at the 11 kilometers a second, which is the critical speed to escape the Earth. Now let's go to, say, Jupiter, right? On the surface of Jupiter, it's around 110 Kelvin, but the escape speed of Jupiter is closer to 60 kilometers a second. So this is why Jupiter and all these gas giants get to hold on to the hydrogens and heliums on them. So coming back to our points over here, right? If the velocity of gas is less than the escape speed, that gas will probably stay on the planet. It's not definitive. You can have stray instances of cosmic particles, solar radiation, heating up those gas molecules just enough to get over the edge and escape. Now, to put a limit on it, well, how much slower than the escape speed you need to be going? We say it's about a 6. If the gas molecules are about a 1/6 of the escape speed of that planet will keep that gas in its atmosphere. So, re-emphasizing here, the low planets will have low escape velocities. The moon's only around 2.4 kilometers a second. So the low mass and or combination of the hot planets, they all lose that primary atmosphere, that hydrogen-helium atmosphere from the initial creation of the planet when it initially formed. And the solar wind can free up gas molecules out there. The solar wind comes in and gives these things just enough energy, enough of a kick that they can escape. So if we lost all of our primary atmosphere, then what the heck are we breathing? We're breathing in a lot of gases right now. It's the only thing keeping us alive. That's what we call our secondary atmospheres. They came from all sorts of different sources. Predominantly, these atmospheres were gases that were trapped underneath the planet's interiors. And seismic activity, volcanoes, liberated those gases, released them, get those gases up into our atmosphere. Now, these heavier types of elements, these heavier molecules, they're not going at the escape velocity. So these secondary atmospheres would stick around. Additionally, comets or asteroids could have deposited some material. We suspect a lot of the water on Earth came from a comet crashing in. And so the massive terrestrial planets, Venus, Earth, Mars, they got to keep these secondary atmospheres. Whereas Mercury and the Moon, they even lost those secondary atmospheres. So the emphasis here, the key takeaway here, is that the secondary atmosphere came from deposited material or was underneath the core, underneath the surface of the planets, and they were liberated later in the planetary's life. And these gases were slow enough, cool enough to not float away. And these are the atmospheres that we breathe today. So the terrestrial planets that are volcanically active, Venus, Earth, and Mars, or at least at some point they were volcanically active, liberating these secondary atmospheres. Comets could put some water there. That volcanism probably produced a lot of CO2, and that will result in what we'll later describe as greenhouse effects, greenhouse gases, warming up the surface of these planets. Altogether, though, the atmospheres of the secondary atmospheres of these three planets are going to end up looking very differently. So the surface gravity on these three planets can define crucially what elements stuck around, what gases stayed there, and what are some of the things we observed. Let's see here. Let's look at the surface temperature. Earth is floating around a nice, comfortable 288 Kelvin, or 20 degrees Celsius. Is a nice warm day for us. Mars is a lot colder, about 70 degrees Celsius colder than it is on Earth. But let's look at the range of things that we see there. In terms of the percentage of gases in the atmosphere, Mars and Venus are almost entirely CO2. That's the largest source. Whereas Earth, it's actually not oxygen that's the predominant source of atmosphere. A lot of people have that misconception. It's nitrogen, specifically N2, that is the most abundant thing in our atmosphere. About 78% of Earth's atmosphere. Every time you breathe in, about 80% of that is just nitrogen that you don't really interact with. You breathe it in, breathe it out. All fine. Comparing the densities or the atmospheric masses of these planets, put this in perspective. Earth has about 200 times more atmospheric mass than Mars. That just means how massive the gases on these planets are. Whereas Venus is almost 1,000 times more atmospheric mass than Earth. You look at the corresponding pressures. If we measure in the unit of bars, not an SI unit, but 1 bar of pressure is about what you're feeling right now as you're watching this video. Mars has 0.006 bars of pressure, whereas Venus has 92 bars of pressure. This is equivalent to swimming several meter depths into an ocean floor and feeling that pressure crushing in, caving in on you.